Hello everyone, and thanks for joining us today. Let's go ahead and get started. Today's webinar is on final elements and proof tests. For those of you that have not been to one of our webinars before, my name is Loren Stewart. I am a CFSE here at Exida. I mostly work with our mechanical customers. So I help valve and actuator solenoid manufacturers get certified, but I also work on our other side of the business and help with training and our end user side as well. For those of you that don't know about Exida, I like to say no matter where you are or where your customers are, we have somebody close by to help. And whether that's in functional safety or process safety, alarm management, or cybersecurity, we have people close by. And these are just some of our main offices. We actually don't have our smaller locations listed on this map. Exida is involved in the complete supply chain of functional safety in multiple different industry sectors. So whether you are an OEM who requires that product certification, the whole way through to the end users using that certified product, we have tools, we have consulting, we have engineering services, we have support, we have certifications, all type of things to help you out. With our engineering and our consulting services, not only are we experts in functional and process safety, but we also have experts in alarm management and cybersecurity. We also have engineering tools. We have great software that really was designed to help save you time and money, and they do that because it really increases your efficiency and your productivity. And we're actually going to look at a couple of our tools in this webinar today. So you'll hear more about this later, but if you're trying to do PHAs, LOPAs, SIL selection, verification, if you're trying to do FMEDAs or alarm rationalization, risk assessments, we have tools that really will help streamline the process for you. We also have certification. Some of you might be familiar with Exida certification already. If you're not, well, welcome. We have certification in IEC 61508 and 511. We have ISO 26262, A-Secure, cybersecurity certification, machinery, and personnel certification. But let's get into why you're really here today. And it's to talk about proof testing and final elements. We're going to cover a lot today. I'm really excited about it because proof testing is so important. It's such an important part of the management of your safety instrumented systems and your safety instrumented functions. It's a very important topic. We're going to talk about why proof testing is important for your system. We're going to look at the calculations, including PFDavg calculations and SIL calcs. We're going to talk about how proof testing is, what the main purpose are, and look at real life examples today as well. So to start us out, I like to start with an absolute clean slate and define what we're first talking about, because if we have different definitions in our head, this webinar might not go as smoothly. So IEC 61508, the umbrella standard, defines proof test as a manual periodic test performed to detect dangerous hidden failures in safety-related systems, so that if necessary, a repair can be made and to restore the system to an as-new condition or as close to that as-new condition as possible. Well, Exida liked that definition, but we wanted to take it a step further. So exida says, yes, take all of that information about a proof test, but it's also the purpose of that proof test is to detect any failures not detected by automatic online diagnostics. And those failures can be dangerous failures, they can be diagnostic failures, parametric failures, failures to detect any unauthorized program changes. So yes, it's all of that, but the main reason you're doing a proof test is to find those hidden dangerous failures. And it makes sense why you don't want to detect the failures already found by automatic diagnostics. If you're already running those diagnostics all the time, they're going to find so many failures, but that proof test needs to find the ones that the automatic diagnostics won't. If you're already checking for certain failures, don't waste your time and don't waste your money rechecking those portions of the dangerous failures. We're going to talk more about how to make your best proof test coming up. But because proof testing is such an important part of your SIFs and your SISs, we're going to look at the reasons why. And IEC 61508 and IEC 61511 actually requires proof tests, and the more and more that they're requiring it, the more and more end users are implementing proof tests. But with more people implementing proof tests, more confusion on when to do it, what coverage, your efficiency, what can be claimed for your proof test. So we're going to look at all of that today. But let's start on your proof test when you are first thinking about your proof test. There's two main categories that you need to consider. You need to think about both the functional requirements and the performance requirements of your SIF. So say you have a simple SIF, say you have a sensor, logic solver, solenoid, actuator, ball valve. Sit there and think, well, what are the functional requirements? What does the SIF actually need to do? Say there's a problem and it needs to shut down the process. What does your SIF need to do? Does the sensor need to detect something? The logic solver need to figure out it needs to act? And then the actuator needs to close the valve. So the functional requirements would be that valve closing. It will shut off the process flow. Great. Is that all of the information you need? No, you need also to consider the performance requirements. What do you need to know about that valve shutting? Well, is there any leakage that's acceptable? Are there any timing requirements? For example, you might have a final element that needs to close per the standard IEC 60534, class 3 leakage within 180 seconds. That has a lot of great information that you need to consider when you are designing your proof test. If the leakage is important for you, if you're a tight shutoff application and that leakage is very important for you, then you need to consider testing for leaking when you're doing your proof test. What if leakage is not important for you? Then don't worry about it, but your timing might be very important. You might have to close a valve within a certain amount of time, and that might be very important. You might want to time a valve. So it depends on what is most important in your SIF design to what you need to design your proof tests around. And always, when you're considering how to design your proof test, take a look at every single piece of equipment in your SIF and look at their safety manuals. Do they have any exceptions to the rules? If they do, they will be in the safety manual. If there are environmental exceptions or restrictions, if it's supposed to be cabinet mounted, or if it's made to be a subsea valve. All of this information will be listed in the IOM or the safety manual. And always check for exceptions, because if you have a subsea application, you don't want to be using a piece of equipment that's only suitable for a cabinet mounted application. When we talk about proof testing, one of the main reasons it's so important is because proof test effectiveness, proof test duration, proof test effectiveness or intervals, all of these variables go into the PFDavg calculation. And the PFDavg calculation, for those of you that might not be familiar with it, it's one of the calculations that can determine your safety integrity level for your SIF. So it's very important to know these variables and to have realistic values for these variables. And we will talk about having realistic values for these variables later on in the webinar as well. I'm a visual person, so I like to see pictures, I like to see graphs, but this is how what I think of when I think of PFDavg. So if you hear PFDavg or the probability of failure, what we're talking about is this graph right here. Here's my little laser pointer. So as time goes on, you have a higher probability of the chances of failing. So as time continues, your chances of a failure occurring increase. So say this goes on until you get to a point you're thinking, okay, now's a good time for a proof test. What does a proof test do? Well, at that point, you are trying to find any dangerous, undetected failures, right? If you detect anything, you'll then get it repaired to an as new or close to as new condition as possible. If you do that, what are the chances of, or the probability of failing? Well, if you're back to an as new condition, you're down to this point here. And then you can continue the cycle again. As time goes on, the probability of failing increases until you get to the point you're going to proof test again. If there's no problem, great, there's no problem. If there's a problem, you're going to fix it. You're back to as new conditions, right? When we talk about the process industry, you don't hear the probability of failure. You hear the average probability of failure, or the PFDavg. What that comes into play is you don't know when your failure might occur within the lifetime. It could happen at this point. It could happen at this point. So the standards allow you to take the average, and that is the number you use in your calculations and those important SIL calcs and those tables for the standard. So this is great if you find everything and you fix it and you find all of those dangerous undetected failures and you are perfect. But what if you're not perfect? Is anything really perfect in life? I certainly know I'm not. So when you think of an ideal or a perfect proof test, ask yourself, is everything tested? Well, what if you run a functional test and you see that the system responds? Then everything works. There's no problem. It's perfect, right? Is everything really tested? Think of your SIF you have right now. Think of one of your SIFs. If you just do a functional test, did you test everything? Let's say, for example, we have a pressure sensor, and we're going to isolate it and we're going to pump it up so that the sensor pressure exceeds that trip point. You have a remote actuated valve and you actually observed that it moved. That's more of a proof test than a lot of people do. A lot of people would say, well, it's remote actuated, I'm not going over there. I saw that it will trip, that's good enough. So let's say you went and you saw the valve move. Did you test everything? Well, you don't know if the seat, the valve seat, if there's a chunk of it missing. It might not allow it to seal properly. Well, what if you didn't measure the response time? What if there's a component failure causing that speed to really slow down? What if that's important to you? Well, you didn't check process connections, a sensor could be failed. You didn't check power supply. You don't know if there could be some limiting maximum current and it could disable your diagnostic alarms. What if leakage was really important? You need that tight shutoff. You didn't check any of that. So as you can see, there are many things that have not been checked, even though you've done a function test. So you're not in a perfect proof test, even if you've observed the valve moving. So let's get more realistic. Let's say what a realistic proof test is instead of a perfect proof test anymore. And that realistic proof test is your proof test effectiveness. That variable is going to be your CP of T. And that effectiveness is going to be a number, it's a percentage. How effective are you? From 0 being you're not doing any proof tests at all, to a 100%, meaning you found every dangerous undetected failure out there. You're perfect. And this is going to be for the mission time. And that mission time, it can either be the lifetime of your plant, if all of your pieces of equipment are going to be for the entire lifetime, or it can be the lifetime of that valve or actuator. If you are planning to do a major overhaul and replace the parts in 10 years or in 15 years, whatever that mission time is. So as you can see here, for your mission time, you're going to have multiple proof tests within your mission time, or that the lifetime of that valve or actuator, or the lifetime of your plant. So as your time increases, your probability of failure is going to start to increase just like it did last time. At this point, once again, you're going to do a proof test. However, instead of going down here where we assumed we were perfect, we're now smarter. We know we're not perfect. We're only going to go down the certain percentage of your effectiveness. This looks like it's about 75%. So you are 75% effective in your proof test, which is still a great proof test. So at this point, instead of going down to the bottom, this is where your next cycle is going to start, until you get to the next time you're going to do a proof test, and so on. And as you might know, the first proof test, you're not going to notice much of a difference or any difference. The second proof test, you might not notice much of a difference. But what happens if you have 5 proof tests in your mission time? What happens if you have 10 proof tests in your mission time? Your PFDavg actually can change. So let's take a look at this. This is what our graph looks like. We are moving on time and your probability of failure. So as you continue on time, we're going to proof test. Instead of going down to 0, we're smarter. We know we're only coming to here. This time, we're going to start at that point. Proof test. Your third proof test is a little higher. Your fourth proof test, we're getting higher. And your 5th proof test, and so on, for the mission time of either your parts or your plant. So what does this mean for your PFDavg? Well, if you were assuming perfect proof test, your PFDavg would be the same as your very first PFDavg. So this is what your PFDavg would come out to. A very healthy SIL3. However, your second proof test, this is the PFDavg of the second proof test. This is your PFDavg of your third proof test. This is your PFDavg of your fourth proof test, and it just keeps going up. So what do? You take the PFDavg of the mission time. And this is your PFDavg that you're actually running. Now, where this comes into be very scary is when your calculations are assuming you have SIL3s in your plant, where in actuality, after the second proof test, you're running a SIL2 or even worse. So the idea of having a realistic proof test can actually make a big difference in your SIL calcs. I promised you examples, so let's look at some. So here, let's consider a high protection SIF. It's a SIL3. We have a single SIL3 level transmitter, a SIL3 logic solver, a remote actuated valve, a solenoid Scotch yoke actuator, certified ball valve, all certified to SIL3. Great. Let's say, for those of you that are not familiar, Excellentia is our tool. There's one of our tools, sorry, and I'm going to show you an example with the SIL verification portion of that. But for this example, we're going to say our mission time is 5 years, and we're going to have a proof test interval for 1 year for that sensor and final elements, and 5 years for the logic solver. And that might correspond with a turnaround at a year that we have, or a shutdown that we have. We have proof test coverage at 100%, right? We're perfect. So here are the results. As you can see, we have our PFDavg. Let me get my laser pointer out again. So for our PFDavg, we are 6.82 times 10 to the -3. And as you can see, where'd my laser pointer go? Anyway, as you can see in the bottom, you can see that SIL for the PFDavg, that's coming in at a SIL2. If you look back up at the top, your risk reduction factor is 147. So it's a pretty healthy SIL2. It's kind of, well, it's a little bit of a low SIL2, but anyway, it's a SIL2. As you can see here, for the logic solver, the sensor logic solver and final elements, we also break that apart for the PFDavg on just their portions of the SIF. And you can see in the pie graph, you can see that most of our PFDavg is taken up by the final elements. But that's kind of what you should expect. Your valves, solenoids, actuators, they're not smart devices. They're simple mechanical devices. So they're not going to have, they take up a bunch of your PFDavg. Anyway, so now let's take the same example, however, change a couple things. Instead of your proof test coverage being 100% perfect, let's be realistic. Let's say for your sensors, we're 90%, and for your final elements, you're 70%. And this time you're going to do your proof test duration. It takes 2 hours with your process online. So let's enter that into Excellentia and see the difference. Well, our calculated PFDavg now is 7.610 to the -2. Your risk reduction factor went from 147, I think it was, to 17. That's barely a SIL1. As you can see, it bumped us straight down into the SIL 1 range for the SIL PFD average. Still, we have most of it coming from our final elements, which is expected, but just changing your assumption from 100% to 90 for the sensors, which is common, and 70 for final elements, which is again is common, takes you to barely making a SIL 1. So as you can see with these real life numbers, it can be a little unnerving. So what is that proof test effectiveness really? Well, we talked about it. It's those percentage of those dangerous undetected failures. It's going to be that range. It can be anywhere from 0 to 100%, but you're going to find it typically between 40 to 90%. Once again, this is your manual proof tests are done not to detect things that you've already found in automatic diagnostics. Try to build your proof tests around those dangerous undetected failures that you're not detected by automatic diagnostics. What does that mean? Well, the better automatic diagnostics means the lower manual proof test effectiveness you're going to have. Well, what does that mean? Well, like I said, I like examples. Let's say we have two products. And both of these products have 100 fits dangerous failures. And you're going to use the exact same proof test for these. For those of you that might not know, fits are failures in time. They're the unit of measurement for failure rates given by the standards, and they're in 10 to the negative 9 hours. So they're very, very small numbers. So we have two products, and you're going to do the same proof test. The first product you have, let's say that has poor automatic diagnostics, and you're going to have a proof test coverage of 80%, whereas product 2 has good automatic diagnostics with a proof test coverage of 20%. If you just had that information and you didn't know more, you might make an assumption on what's safer or what's more reliable or even what to purchase. But before you make your decision on what's better, look at what you're left over with. So for product 1, it has poor automatic diagnostics. Of those 100 fits, 10 of the dangerous failures will be detected, so that dangerous detected rate, where 90 of the fits are dangerous undetected. So those 90 fits, 90 are left over, kind of hiding. So you do a manual proof test of product 1, and it detects 72 of those 90 fits. You have a proof test coverage of 80%. So you might think, oh, 80% proof test coverage, that's great. Well, from those 90 fits, 18 fits were still undetected. Okay, let's look at a good automatic diagnostic. So same 100 fits. 90 of those fits are going to be detected, where only 10 are undetected. You do your manual proof test, and it detects 2 of the 10 fits. Your proof test coverage is 20%. You might say, oh, that's not a good proof test coverage, but only 8 fits were undetected. So between the difference, 18 to 8. So make sure you are comparing apples to apples, and don't just compare proof test coverage. Make sure you know the automatic diagnostics when you are comparing proof test coverage, if you are comparing just proof test coverages for the two products. And never use just proof test coverage as a measure of quality of a product. Usually the opposite is true. You want good automatic diagnostics. You don't want to rely on your manual proof test coverage when you're picking products. So how do you determine this proof test effectiveness? Well, if you are using certified products, proof test effectiveness can be given to you by the manufacturers. If the manufacturers give you they will give you proof test instructions and say, if you follow this set of instructions, you will have a proof test coverage of this percentage. You will find this many of those dangerous undetected failures left over. If you don't buy certified products and you're doing this on your own, you need to determine the effectiveness yourself. So you have to kind of take it a step further. You need to establish a reasonable baseline failure rate for the device. And then you need to do an FMEDA, a failure mode effect and diagnostic analysis with appropriate functional failure modes. You're going to then, once you have that done, assign a coverage as a function of those failure modes and the test, and then allocate between the diagnostics and the proof test. And to do this, there's a tool out there. This is one of our newest tools, so I am really excited to show you this in my webinar. It's the FMEDA tool. It can let you do a FMEDA if you want to do your FMEDA. And to do that, you will have your bill of material, you will have your drawings, and you will add part by part and consider how each part will be affected if it breaks, if it binds, if it leaks, if it gets stuck, if it shears, if it bends, and if it will lead to a dangerous situation or a spurious trip situation. At the end, you can then say your diagnostics and evaluate the proof test per the FMEDA. And you can make it easier if you have a FMEDA tool. When you are considering your proof tests, we have thought about different ways of doing proof tests and the effectiveness. And especially when it comes down to final elements, we define 5 major levels of proof tests. And just like your safety integrity levels, each level, it gets a little tougher, right? So your level 1, you're going to have just your partial valve stroke test. Let's say, for example, you have a floating ball valve. Let's say you do a stroke test on the valve. If you have a floating ball valve, if you just do a partial valve stroke test, you might just move the valve 5% or up to 15% of the stroke, just to show that it can move. You broke any binds, any stiction, any corrosion. You're showing that the shaft is attached and it can be moved. The next level of proof test is a full valve stroke test. So say you have your floating ball valve, and instead of just moving a tiny bit, you are doing a full stroke test. You are completely moving that ball valve. This will let you know that it can't just move a little bit and then get stuck. This will let you know even more failures or those undetected failures that might be there. A full valve stroke test will let you see if the ball can fully close or if it only gets part of the way closed. The next proof test, the next level of proof test is proof test 3. It's taking that full valve stroke test but doing it in operating conditions. This will let you know if there is going to be any leaking. This can be important, especially if you have a tight shutoff application. The next proof test, or sorry, that was at operating conditions. Proof test 4 is adding that leak test. The operating conditions is just letting you know that it can withstand the pressure, the temperature, all of that information. Then you have your final proof test 5. When you do everything under the sun almost. You're doing a full valve stroke test. You're doing it at operating conditions with a leak test. This is obviously going to let you know if most of the dangerous undetected failures compared to the other proof tests. So what does this look like with real life numbers? Well, I went in our Excellentia program and I created a really simple SIF. I chose a solenoid, a poppet valve, an actuator, and I think it was a ball valve. And I looked at what the dangerous total failure rates were for each of these. Then I did an FMEDA for each of the solenoid, the poppet valve, the actuator, the valve, and the assembly accessories. In that I included any mounting or coupling. And I considered what it would be like for each proof test level on each device. And I considered what dangerous undetected failures would still be for each device. So, for example, I did proof test 1. Remember, that's your partial valve stroke test. You're just moving it just a little bit of the way to break those bonds. For your solenoid, you still had 43 dangerous undetected failures. For your poppet valve, you had 6. Your actuator were 287 dangerous undetected failures left. Your valve had 315, and your mounting and coupling were 28. So, just doing your partial valve stroke test, you were able to find 57% of those dangerous undetected failures, which is great. You found more than half of your hidden dangerous failures, things that were lurking underneath the surface, just waiting to cause you problems. So as you can see, just doing a partial valve stroke test, you are really upping your game. But you want to take it a step further. 57% is great, but what about 74%? All you have to do is take it from a partial valve stroke test to a full valve stroke test. You want to up it even further? Add operating conditions. What about proof test 4? Proof test 4, that's a big jump from proof test 3 to proof test 4. Why is that? You're adding your leak test. So all those dangerous undetected failures that are contributed to a leak have been found. Well, what about proof test 5? You're not only doing a full valve stroke test, you're doing it at operating conditions with your leak test. So what is left over? At proof test 5, you're doing almost everything you can. There are only 4 dangerous undetected failures that are left over with your solenoid, only 1 with your poppet valve, 5 for your actuator, 5 for your valve, and only 1 for your assembly accessories. So out of all of those dangerous undetected failures, there are only 16 left over in your SIF. You have found 99% of your dangerous undetected failures. That's awesome. So even with this, you do a full valve stroke test at operating conditions with a leak test, you still don't find everything. So even if you do everything you possibly can, you're still not perfect. So never assume 100%. But as you can see, you can alter your proof test coverage, your proof test effectiveness, with different ways. And of course, we know that not everybody can do everything. Maybe you can't do it at operating conditions. What if you have to be in bypass? That's fine. What if you have an unstable process and you can only do a partial valve stroke test? That's fine as well. Just know how much effectiveness you are really pulling out and what you do your calculations with reasonable and realistic numbers. So if all you can do is a partial valve stroke test, no big deal. Just don't put you're doing 100% effectiveness in your SIL calcs. Put that 57% effectiveness in your SIL calculations, and maybe you have to do your partial valve stroke test more often, but there are things you can do. Also, don't give up. What if your effectiveness, if you put in your reasonable numbers and it puts you from that SIL 1 or SIL 3 to a SIL 2 or a SIL 2 to a SIL 1, don't get frustrated and give up. There are things you can do to change in your SIF. There's other variables. Shorten up your mission time. If it is a 10-year mission time, maybe it's a 5-year mission time. Or shorten up your proof test intervals. Instead of doing a proof test every year, maybe do a proof test every 6 months. And there are ways that you can alter your SIFs. What if you have to change out equipment or do something more reliable, or change your architecture, maybe have a 1 out of 2 voting? But there are ways that you can still have the safety you need with realistic numbers. And if you have realistic numbers in your calculations, I know I can sleep a lot better knowing that maybe somebody I loved is at the plant close by. So in summary, always use realistic numbers for your PFDavg calculations. All of the variables, not just your proof test effectiveness, your dangerous undetected failure rates, your mission time, always use realistic numbers. Your proof test coverage can impact your PFDavg. It can impact it by an entire SIL level. So be wary of that, be consciousness of that. You can know your proof test coverage by FMEDAs, by buying certified products or doing the FMEDAs yourself and evaluating the diagnostics and the coverage in the FMEDA itself. You can do that using tools, which makes your life a lot easier, or you can buy certified products. And we know you might not be able to do your proof tests at operating conditions. You might not be able to include a leak test, but do what you can and just use realistic numbers. If you loved this webinar and want information, this is actually a part of the new book we released, and I'm really, really proud of sharing this with you. I'm one of the authors. Final Elements in Safety Instrumented Systems. This was just released, I think it was last week, and it's available on our website and on Amazon. And this book talks all about final elements, and it's divided into 4 major sections. We talk about functional safety and final elements, all of the equipment used in final elements. So if you want to know more about valves, actuators, certain different types, this is a great book. IEC 61511 Compliant System Design, so how you use those pieces of your SIF in a compliant design, and also the product development compliant process. And yeah, this book covers the entire functional safety life cycle and reliability requirements. So if you loved this information and you want more information on valve and actuator and control technology and their strengths and weaknesses, check out the book. You can preview the book online too. It's pretty cool. So now I will go ahead and take questions. If you have any questions, And if you think of questions later on, feel free to email me. There's my email address along with our website. If you like this information and what more, we have white papers, we have books, you know about our free webinars, we have blogs, all sorts of fun stuff. Okay, we have one question about bypassing. If you have bypass in a line, do you need to proof test the valves on the line, or proof test the valves on that line, or just the main line? Well, for the SIF itself, the SIL calculations depend on the ones that are going to be used. So you technically just need to rely on the main line. However, if you are counting the time you have in bypass, you can do SIF calculations considering your bypass. We have webinars on the PFDavg calculations, and that's one of the variables. I always would want to proof test the lines while the bypass lines as well, because if I'm going to run in bypass, I want to know that they work, but you don't have to. We have someone asking if they have a client who's arguing if they are using generic failure rates, and they did in-SIL verification, and they do a proof test every 2 years, they can assume 100% proof test coverage. What is your advice? Well, you know what happens when you assume. My advice is that you could definitely use generic numbers in your SIL verification. Absolutely, the generic numbers are going to be more conservative. So I'm thinking that's where they are saying that. However, I wouldn't use 100%. I would definitely use a more conservative number than 100%. Without doing the SIL verification myself, I don't feel comfortable saying that proof testing every 2 years is even going to work with that. I would take a look at the SIL verification and make sure that they are being conservative, because the 100% is definitely not conservative. Okay, we have a question about mission time. Talking about the plant's mission time or the major overhaul of the equipment. It depends on which one you're using. If you're doing a major overhaul, if you're replacing your valves, your final elements, you can use that major overhaul. However, if there are pieces that you're not replacing at that major overhaul, make sure you're taking that into consideration. Don't say that you're doing a major overhaul in 5 years when your plant life is 25 years and you're keeping something in there past the 5-year mark. So there are ways to model that in Excellentia and Silver. And I think that answers the question. In the Silver example, there was a question about the mission time and different mission times for the different pieces of equipment. I have a question on who determines the proof test does the manufacturer or designer? Well, I always say as a manufacturer, I would suggest what I would want my customers to do, because as a manufacturer, they will know the valves, they will know the actuators very well. As a end user, it's how you are calculating it and how you're using it in your system, how you should be calculating it. So if the manufacturer is giving you a proof test saying follow these instructions, this is the proof test effectiveness you're going to get, follow those instructions and you can use that. It really, there's no strong rule if it's the manufacturer or the end user or designer who is using this information, who's stating this information. I have a question. Someone has a certified device and it gives proof test procedures and it's looking for proof test coverage. Where should you look? Great question. The proof test coverage will always be in a FMEDA report. So go back to the manufacturer, either ask for the proof test coverage number themselves. They can either give you the report or give you that number, but it will always be listed in a FMEDA report. If they've done an FMEDA and have been certified per that FMEDA, they will have those numbers for you. And I think that just answered the next question as well. That proof test effectiveness, if an FMEDA was done, you will have that proof test effectiveness. So go back to your product, see if they've done a FMEDA, and ask for that information. Okay, and I have a lot more questions in here, but a lot of them are repeating. A lot of questions about where to find proof test coverage. I'm glad that you guys have asked that question. Always go back to the manufacturer. And if you think of more questions later on, feel free to email me. And thank you so much for joining us today. And hopefully you enjoyed this webinar. And we look forward to seeing you at another time. Bye.